Live from Santa Barbara, it's CS-030, broadcasting live from Winter Hall, part of Mayterm 2018. We are joined with a studio audience. Every day it's a little bit different who's showing up here, thanks to our ability to remote participate. We are part of a 5-week class. My name is Professor Don Patterson, and this lecture is scheduled for 2 hours today. We are communicating live for those folks on our Slack channel on hashtag broadcast question. And thanks for joining us. Thanks for joining us if you're doing it in real time or later if you're watching remotely. Shout out to Boaz, who's on the train somewhere and maybe actually watching this live from the train. That would be super cool. We'll see if that actually comes along. Okay, so let's see. Let's make sure we're here. Even as I was setting up, I was getting nonstop text messages and notifications, and as much as possible, I've turned those off on my machines. We just want to arrive, remember what we're doing, make sure our attention is set up the way we intend for it to be. Just to get us started thinking about our position in the rest of the world, we've been talking a little bit about legal regulations and the way some fall short of what we are called to. Some are too strict than what we are called to, and some permit things that Christ rejects. And we've been talking about this because in a lot of cases in software, as we make software, we find ourselves running into different kinds of legal situations that we have the power to bypass because of our ability to use computers in various ways. And so as a result, there's a burden on us to have some sort of understanding of what's appropriate when we encounter those situations. This is largely because legal regulations take time to catch up with technical capabilities. I think it's worthwhile mentioning, however, that legal regulations aren't the only thing that regulate behavior. And I want to talk over the next couple of classes about a few other things that regulate behavior as well. And a lot of these ideas are drawn from a scholar named Lawrence Lessig, who thinks a lot about, or has written a lot about, regulation in society. We're building up to sort of one of his big conclusions. Another thing that regulates regulates behavior are social norms as well. So one of the particular passages that we looked at from the Bible was Christ talking about adultery and how adultery was against the law at the time. But of course, that's not against the law in our time, and yet it is something that seems really wrong to most people. And you ask yourself, well, why is it that most people tend not to violate a commitment that they've made to another person through marriage or otherwise, if that's not legal? What is it about that causes people to respect a relationship, either emotionally or physically or in different ways? And you could argue that that's because of social norms, that although there isn't a legal regulation that prohibits adultery, there's definitely social pressure in order to not engage in that behavior. Social norms are different than legal regulations, though, because they're a lot softer. They're always being tested and renegotiated. We see that all the time in news and our relationships with other people. But I think it's important to point out that sometimes the things that we do are not dictated by legal regulations, but because of the community that we're a part of and what the norms are in that community. And that those norms have some of the same characteristics of these legal regulations. Some social norms do not require of us everything that maybe Christ would require. Some social norms require more of us than what we're called to. In a lot of Christian communities, for example, prohibitions against drinking alcohol are much stronger than what we're called to in the Bible. There's plenty of alcohol drinking in the Bible by none other than Jesus, and yet for various reasons we impose social norms on ourselves that are stricter. Perhaps because we're in a community that doesn't do a good job of handling alcohol responsibly, for example. There are other things, there are social norms as well that permit things that we wouldn't permit. And so just like in legal situations, we find ourselves having to find a standard that we believe in and that we have support to commit to, also in social norms we run into that same situation. So legal regulations, social norms, two different things that regulate behavior. There's two more that we'll look at going forward, and then we'll sort of try and tie this all together with how that relates to technology. Obviously, there are social norms around technology usage as well, and one of the things that we're constantly trying to figure out is what's the appropriate behavior around cell phone usage. Is it appropriate to use cell phones when we're in a movie theater, when we're at a restaurant, when we're at a family dinner, when we're in a class? it's not clear what those regulations are all the time, and we're constantly having these discussions about what is appropriate in a given circumstance. And sometimes we have that explicitly, and other times we kind of have implicit pressure to behave one way or another way. We're always trying to figure that out. Technology is, in the middle of that. Of course, there are a lot of social norms that don't have anything to do with technology either. But thinking about that a little bit as we go forward. Meanwhile, in the content of our class, the other content of our class, that's also content in our class. We've got a quiz on Chapter 3 to do today and a programming assignment on Chapter 3 due today. Quiz on Chapter 5 due next Monday. You should be looking for a quiz on Chapter 6 to come out. That'll be due next week as well. We're also going to have another programming assignment that's going to be based on JMonkeyEngine, which I'll put out depending on how class goes today. So that's what we're looking for. You can see if you've been following along that we've pushed Chapter 15 forward. The content in the loops took a little bit longer than I anticipated. So we're going to be moving Chapter 15, which is about data structures, into next week. Any questions before we dive into the technical content? Good. Go. All right. So last time we were talking a little bit more about if statements. We were exploring those. We did some examples with those. But mostly what we brought into focus was while loops. And while loops are in many ways structurally similar to if statements. And so I put on the right there the for loop, or the flowchart that describes how a while loop works. And just pointed out that if you think about it in terms of a flowchart, a while loop and an if statement are very similar. It just has to do with whether or not we have that connection down there at the bottom. Let's see if I can point that out. This connection right here, whether it goes back up to the top or whether it connects here. If it were to connect and just drop down, then that would just be an if statement. But because we have the ability to do loops in a while loop, every time we complete our statements, we loop back around to the top and check our condition again. And sometimes if you look at it visually like this, you can see that a while loop is always going to run its condition at least once, but it's not necessarily the case that it's going to run the body of the loop once, because you could immediately get a false answer. You can also see that it's going to run that condition, that diamond, one more time than the number of times that you run the body of the while loop. Either one and never running the statement body, or the number of times you run the statement body plus 1, which is the last time you evaluate it before you kick out of the loop. Maybe it's not quite as clear from that flowchart, but it's something that we talked about, which is that you can get into an infinite loop. And this is the case where the question that you're asking in that diamond never gets evaluated to false. It's true forever, and you just sit there looping forever and ever and ever. The obvious one was just if you checked the true condition, while true. But more generally, if you have a condition in that while loop and you never change any of those variables, then it's unlikely that you're ever going to get out of that loop because there's no change to the system. So that was an infinite loop. And then we also mentioned off by 1 errors, where we didn't hand trace our loop very carefully, and either we initialized a variable to 0 when it should have been 1, or 1 when it should have been 0, or in our conditional check we used less than or equal to when we should have used the other one. So that's what we did last time. What I want to do now is introduce the idea of a for loop. A for loop is like a while loop, and to motivate it, what we want to look at is one particular instance of a while loop. So what we've got here is a while loop that is going to run through the contents of the loop a certain number of times. And in this case, we're actually going to run through it 10 different times. And the way we're going to do this is we're going to initialize a counter and set that equal to a starting value, which is 1. We're going to have a check that says while the counter is less than or equal to 10, we're going to run the body of the loop. And as we start with counter equal to 1, we're going to run the body of the loop immediately. We're going to print out what the value of counter is, and so you can see the 1 in the output right there. Maybe, hopefully not in front of it. And then we're going to update counter and check the statement again, the conditional again. And we're going to keep going until counter is equal to 10, at which point we're going to evaluate, is counter less than or equal to 10? It is. So we'll run a loop a final time. Counter will be set equal to 11, and we'll kick out of this loop. That's fine. That is an example of a while loop. It's a mechanism for doing a while loop a certain number of times. But this is so common in programming that a different kind of structure is introduced in order to capture this very common situation of going through a loop a certain number of times. And that's what the for loop enables us to do. So if we take a look at the while loop at the top and then the blank template of code at the bottom, I want to point out where the different components of this loop go to and how they work. So the first thing to notice is that we've got this new for loop structure at the bottom. We have the keyword for, we have parentheses as if we were running a conditional statement, and then we have those two semicolons hanging out there in open space, but that's just for the benefit of the slides here. So in a for loop, we have these three different places where we can put code in between each of the, or surrounding each of the semicolons. And so the first thing that we do is we bring in the count, the initialization to that first piece there. Int counter equals 1. We bring our check from the while loop to the middle piece, so counter is less than or equal to 10 goes there, and then we bring our update statement from the bottom to the end. And once we've done that, we have almost exactly the same code down below as we did in the while loop. The code in the bottom is going to run through a loop 10 times, output the exact same code along the way. Now I say it's almost exactly the same for one reason, which is that the variable counter, the scope of the variable counter, is slightly different in these two cases. In the first case, we introduce the variable counter before our while loop, and because we introduce it before our while loop, it continues to be accessible after our while loop. But in the case of the for loop, we're introducing our variable counter in the header of that for loop, and so counter is only known within the body of our loop. But it doesn't get initialized each time independently. There's just one variable counter that maintains its value until the for loop is done, at which point we lose the access to the variable counter. So that's the slight difference. The scoping of the variable is slightly different, but the function of the loop ends up being the same. So let's just walk through those components and make sure we're clear on them. So the first thing we've got is this reserved word for. There's just one new reserved word introduced in this looping construct, although the syntax adds some new complexity as well. We have this initialization. It's only going to be run once, and it'll be run once as we enter into that loop, and it's going to be run once no matter what. So whatever you put there is definitely going to be run. It's definitely going to be run one time. The middle piece is going to be a condition that gets checked repeatedly before entering that loop body. So this is also going to be run at least once and possibly more than one time, although the first one's just being run once. And then finally, the last part is the update. And the update is going to be run at the very end of the loop body. And this might be run 0 times or multiple times, depending whether or not that conditional in the center evaluated to true at some point. The mapping between these different components and the while loop is a real natural way of understanding how it functions. But actually, as someone who's been programming for a little while, when I write a for loop, for some reason, I've learned to think about the for loop on its own, independently of thinking about the while loop. And so I think that comes over time. So as I would write code in this situation, in my head, I would say something like, for int counter equals 1, while counter is less than or equal to 10, counter plus plus. I kind of think that in my head, and I understand how that's being mapped into the flow of the structure. And I never actually refer back to the structure of the while loop, although there's a really natural mapping between the two. So the last thing to point out is that this variable here is local to the loop body. So obviously counter has to persist across multiple runs of the loop because we're incrementing it. And so we can't be creating the counter each time we go through the loop body, or that increment at the end of our for loop wouldn't be working. But if we try and use counter outside the bottom of the loop, we're not going to have access to it. So it's almost like counter exists in this intermediate scope between outside the for loop and inside the for loop. There's this intermediate scope that is the entire duration of the for loop and no longer. Okay, so what I want to do is I want to enter this code into Eclipse and then walk through it in the debugger just so that you can see the structure being executed as we go through it. And I think this one we can do without sharing at this point. We'll share in a little bit. So let's switch over to Eclipse. And let's create a new class here. Shut down what we've got. And I'll just make a new class for us to work with here. And I'll create a main function just so that we have some place to run some code. Great. All right, so what we proposed is for int counter equals 1 while counter is less than or equal to 10, we'll do counter plus plus. And then we're going to output it. So system.out.println and counter. And just to make sure we believe everything's going okay, we'll run that as a Java application. So it will run the main loop. And we can see that at the bottom here in our console, we get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 on different lines. That's kind of too much to see. It's taking up too much screen real estate. So I'm going to put it all on the same line. And I'm going to put a space at the end of it as well. Let's try running that. Okay, so now we have a little bit more clear there. All right, so what I want to do is I just want to step through this loop, and I want to demonstrate how counter is being updated. So I'm going to put a debug. Actually, let's we'll put the debug right there. And then we'll debug it as a Java application. We'll switch over to our debug view. Well, actually, for consistency, I think I'm actually going to stop that for a second. And I'm just going to make this into integer, because that's what we've been working with in this class. Let's try debugging that again. All right, great. So I've just debugged the, I've started my program in debug mode. I've put a breakpoint on line 7. My program is now stopped, and I can see that because up here in the debug panel, I can see that I have a Java application that's running, and I can see this little pause symbol right here. And if I double-click on where it's paused, the code will be highlighted where I'm currently stopped. And it says line 7, so I can see line 7 right there. And if I look up here under the variables that are currently known, you can see that counter doesn't exist yet. That's because I haven't actually entered this for loop. But as I step over that line, I now see that counter has been initialized and set equal to the value of 1. And that's because we've run this first bit of code before we enter into the loop. Well, since we've entered into the loop, it must also be the case that counter is less than or equal to 10 has been evaluated. That evaluates to true, and so we do enter into the loop. So now we're at line 8, and I'm going to step over that line, and we can see that the result of running system.out.print executed, and now we've outputted line 1. We return to line 7, where we are about to run the update line. Because of the way the debugger works, we're going to run everything at once. We're going to update counter, and we're going to check whether or not counter is less than 10. And if it does pass that check, then we're going to move into line 8 again. So both things happen. We updated counter, so that got highlighted in yellow to indicate that something changed since my last step. We can see that the value is now 2. Because we have entered into the loop, we know that it was evaluated. The evaluation of counter less than or equal to 10 ended up being true. And in fact, we could drop this over here if we wanted to. And we could add a new expression. This is left over from another project. And we could add a new expression and just say is counter less than or equal to 10. And if I had enough screen real estate, we would see the answer to that. There we go. So as we're running, we will see that expression get updated as is appropriate. So now we're on line 8, counter equals 2. We're about to output counter. I'll step over that line. We now check out the for loop again. Counter is still less than or equal to 10, but we haven't updated yet. Counter is still equal to. We're going to update and then do our check after we do our update. There we go. Counter equals 3. We continue doing this. The process remains the same, and things become interesting then once we get to 9 or 10. So now counter is equal to 9. We're at the header of the for loop. We're going to run our update, so counter is going to get assigned counter plus plus, or counter is going to equal counter plus 1, so 10. We're then going to run the check. Counter is less than or equal to 10. It is less than or equal to 10, so we're going to drop into the body of the loop one last time. We're going to output that, and then we're going to return back to this top of our loop. Counter is still 10 at this moment, but if I step over this line, we're going to update counter. It's going to become 11. Counter is no longer less than or equal to 10, so we won't run the body of the loop anymore, and we'll proceed down to probably line 10, is what the debugger will give us, having not run system.out.print any more times. So step over. Great. Now you can see if you look up in the variables that counter is now gone. Counter isn't known to any code once we've left this for loop. That's an important way in which the scoping of counter is limited. You can see also that when we try and evaluate in our expression, is counter less than or equal to 10, we get an error because counter's not known anymore. So that's just not going to be something that's helpful. So it's not harmful to have it up there, but we'll just erase it for the time being. All right, we'll go ahead and run out the program. There's nothing else to run. Our program's done, and we've seen a for loop in action printing those different components out. Any questions about the details of what's happening in that for loop locally? Anyone out there on Slack? Okay. So a for loop is very flexible. What we saw is that we saw the way in which it maps from a while loop into this for structure, and it naturally makes sense to count through a bunch of numbers a certain number of times. But those different expressions that we have at the beginning, in the middle, and the end can be anything. And if we're creative about what things we put in there, we can do different things in our loop that maybe isn't immediately obvious. For example, one thing that we can do is we can count down. We don't have to go from 1 to 10. We could also go from 10 down to whatever we want. So how do you guys think we would go about doing that? Great. So taking what we've got there, we can duplicate it. So let me put that down below. I'm going to put a print line here so that we have a break between our output with no content. Okay, so that's just going to print our first bit. All right, so now we have another loop, and we want to use it to count down. So when we initialize counter, we won't initialize it to 1, we'll initialize it to 10. Our check now is not whether it's less than or equal to 10, but whether it's maybe greater than or equal to 1. Let's just keep it consistent with our previous example. And then instead of doing counter plus plus, because if we did counter plus plus, our for loop would never end. We would just continue increasing counter, just like a while loop would never end. A for loop can have an infinite loop as well. So instead of subtracting 1, we'll do minus minus, and that is the same as saying counter equals counter minus 1. And I'm just going to put a different version in there so that you can see that it's kind of flexible about what code you actually put in place there. I'll copy our new line character there so we get a new line at the end. And if we run that code, we'll get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then below it, we get 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Pretty good. What about skipping numbers? What if we didn't want to hit every single number, but we wanted to do every other number? How could we alter our for loop to do that?
If we started with even numbers, then we could say we put like an if statement in there to say like if they can be divided by 2.
Huh? Okay, let's take a look at that solution. So let's say we just wanted to do even numbers here. One suggestion was that we would just check if counter mod 2 equals 0. Do that and print something out. How would that work out for us? Give a little space there. Okay, pretty good. Get even numbers. Any other ideas about ways to tackle that? Can we do it just by using the header of the for loop?
Oh, yeah. Shoot. No, -2. Counter -2.
There you go. Great. So that's an alternate way to do it. Get 10, 8, 6, 4, 2. Now, they have slightly different pros and cons, right? So if our goal is to get all the even numbers, it's up to us to make sure that we're hitting even numbers if we do it in the for loop in this way. If we did it with the if statement and a mod, we're sure that we're only going to see even numbers and we don't have to think too much about it. The downside of doing it with the mod, though, is that your loop is actually going to go through the iteration 10 times. So you'll actually go through and check all those conditions 10 times, even though you'll only print things out when the loop variable is even. The benefit of doing it this way is you're only going to go through the loop 5 times. Yeah, 5 times. And so you're going to do half the work. Not quite half the work. A little bit less than half the work. But you're not doing extra work, that's for sure. Does that make sense? The difference between a loop in which you're running every single iteration of the loop and filtering out ones you don't want versus count equals count minus 2, you're only running 5 loops. Okay, so just to make it clear how the variable scoping works, I want to demonstrate how counter is known and not known, and what you could do if you wanted to know the value of counter afterwards. So if we come down here and we decide that what we want to do after we print out our free line, we want to say that counter ended up being Eclipse gives us an error. The error that says is counter cannot be resolved to a variable. That's because the scoping of counter is only within the body of the loop. So if we put the same code right there, it works fine there because it's known within the loop. But what if we actually want to know counter? What if we would like to know what the value of counter is beforehand? Well, then we have to declare the variable outside the scope of the loop. We have to make sure that even if we initialize it in the loop body, it has to be declared in a broader scope or a bigger scope. So that's easy enough to do. We just throw integer counter in up here and break the declaration there. So we just separated out the declaration of the variable and the scoping of the variable from the actual initialization by bringing integer counter out to outside the for loop, even though we're still doing the initialization in the for loop itself. And now you can see that counter is resolving fine. We're not having any trouble getting scoping there. So depending on what you're doing, you might need access to that variable, you might not. If we did this, we could actually use the same variable multiple times in each of the loop. Now we've declared counter once, and that same variable is being used here and here and here. But it's a different variable up here. Even though it has the same name, it's being allocated just within the body of this for loop. If we wanted to use the same variable all 3 times, we could go up here and declare the redeclaration. And you can see that when we tried to declare it again here, we're getting this error from Eclipse, and Eclipse says duplicate local variable. So if we did try and do this, Java through Eclipse is saying, well, you can't have 2 variables named the same thing. If you do, I don't have any way of knowing what you intend to update or what you intend to increment or what you intend to test, because if I allowed this to happen, then there would be 2 places in memory with the same name, and I don't know how to resolve that. So to prevent ambiguity in that case, what happens is that you get an error. Now notice that behavior isn't always consistent, because if you had an instance variable called counter, the local variable would shadow it, would block it. So these duplicate names have different effects in different situations. Okay, counter within the body of the loop. Good? Oh, one last thing to point out is that you could also have variables that exist solely in the body of the loop. We've seen this before. So in this case, we're just going to end up printing out the same thing that we had before. We're just doing it in a different way. Printing, oh, sorry, I don't want to debug. I just want to run. So we end up printing the same thing. Instead, though, we're accessing it via a variable x. Now, the difference between what we've got here, let me move us back into this, where we have this place. Now, the difference on line 17 and line 18 is that counter is being initialized and created. It's being declared and initialized. It's being declared, created, and initialized in line 17. And that one counter variable is consistent and persistent across all iterations of the loop. But the variable x is local within the body of the loop. And so x is being created brand new each time you go through the body of the loop. So x is being created on line 18, and it's being destroyed right after line 19 is run. And so that's a local variable, but it's local within the scope of the loop. So you can see that we have these interesting differentiations of 3 places where we can have scoping of variables. Y is persistent, outside of the loop, before, during, and after. Counter is 1 variable present through all iterations, and Y is going to have several instantiations throughout each loop body. Okay. All right, let's clean up our code. Another thing that you can do is maybe you're not just interested in working with the numbers, like these count numbers. Maybe you're actually interested in working with some data. And so we can use those count numbers as indexes into data that we maybe already have. And so we can use those loop numbers that we're generating, not just for themselves, but because we want them to be addresses of something else that we're interested in. So for example, we could look at each character in a string, and we could use a for loop in order to do that. Let's take a look at what that would look like. Give us some space here. All right. So let's say we had some string we're interested in. Joy, what is it? What's the contents of our string today? Okay. My daughter's named Joy too, and she gets tired of things like that. All the Christmas jokes. All the time, yeah. That's okay. So this is our string. It is stored in a variable called data. It has punctuation. It has capital letters, lowercase letters, and spaces. And maybe one thing we would like to do is we would like to print every character in this string out, but on its own line. So write the string out vertically. So what we can do is we can create a for loop where we have a variable that's going to walk through each element of our string. So I'll call it index, just to indicate that we're going through each of the indices in the string. We're indexing into each character in the string. And we're going to start at 0 because when we look at the first element in a string, it's index 0. Right? That's a fun fact of computer science. Our first element is almost always 0. All right, we know that we're going to want to continue looking at each character. We're going to want to continue doing this loop as long as index is less than the length of data. Now this is a good place to think about our off by 1 error, but before we do that, let's say that what we want to do is at the end of our loop, we want to update index. All right, we'll come back to that off by 1 error in a second. We know that what we want to do in each instance, though, is we want to print out 1 character of our string. So now what we're going to do is we're going to use index not to print out the number, but we're going to use it as a way to get access to the sequential elements of our characters. So there's a method in string called char at, meaning character at, and then at a particular position. And so we'll just say we would like to print out the character that is at position index as we walk through this loop. And then the last thing we'll do is we'll print out a new line character as well. So now let's comment out the code above it so we don't... Where is the new line character? The new line character, because I'm calling system.out.println with no input, all it does is print out a new line character. It's outside the loop, so we're going to have 1 extra one at the end, but it's also internal in the loop. So we're going to print each character in a new line, each character in a new line, and then when we get to the exclamation point, we'll print exclamation mark, new line, new line. So we'll actually put a blank. Ah, right. Okay, so if we run that, down in our console, we don't see it all because it needs scrolling. We see joy to the world separated out on each one of the lines. Now let's think about that for a second. Why didn't we use less than or equal to? Because certainly we want to get the last character, but we did get the last character. So why did less than data.length allow us to print out the last character? And what would a data less than or equal have done to our loop if we had done that? We can try it. No harm trying it. We get this exception. We get a crash. And the crash says string out of bounds exception, string index out of range. We gave it 17. Well, it turns out that Joy to the World has 17 characters in it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. But the first one is 0. So if we want to look at each one of the characters, we look at 0 up through 16, even though the length is 17. And so it's a pretty common practice to start your index at 0 and go while you're less than or equal to the, go while you're less than your length. And if you look at each character from 0 while you're less than the length, you're going to get the entire thing. So this is a great example of an off by 1 error, because you very easily could have thought maybe you should do something like this, in which case you would have gone off the end of your array. You might have also thought you should have done something like this, in which case you wouldn't have gotten the first one in your array. You might have also thought, in some cases, you find yourself doing something like this. You would have missed the last character in your array. But if you had done this, that would have been fine. Because data.length is 17, minus 1 is 16. We run through our loop as long as index is less than or equal to that. Over time, it'll probably become more natural to just do this pattern. It's concise and it's consistent with the indexing starting at 0 and the length being the actual number of characters that are present. All right, so that's a reason why we need to be able to pick particular sequences of numbers. We need to be able to go through and identify numbers like 0 to 16 or 16 to 0. What if we wanted to print out the string backwards? How would we do that? Well, we could do that by starting our index at data.length minus 1, because we want to start at 16. We want to continue while it's greater than or equal to 0. And instead of incrementing our index, we want to go down. Instead of doing a new line each time, we're going to print on the same line. And then the result is that we reverse the string. So the reason why we were able to reverse the string is because we were able to control the order of indices that we were using in order to jump through there. We could print every other character. We could do a lot of different things in this instance. Okay. Previously, in our last episode, Professor Patterson was looking at bank interest. He was very interested in knowing when the bank interest was going to be double the target interest rate, double the starting rate. But in a for loop, we could frame that question a little bit differently. In a for loop, we could say, rather than asking how many times or how many years is it going to take to double our balance, that was a real natural question for a while loop. Instead, we can say, what is our balance going to be after X number of years? Because we know the number of years, that's a much more natural mapping to a for loop instead. So if we wanted to compute the growth of our savings account over a period of years, we're going to use a for loop because the variable year starts at 1, and we can control that in constant increments. And so what we'll do is we'll do a loop that looks something like this. Notice we're being careful about our 1s and 0s and our less thans and our less than and equals. So we're starting at 1. We're saying year number 1 while we're less than or equal to the number of years. So if the number of years is 1, we're going to run through this loop 1 time, which is what you want. If the number of years is 0, we're not going to go through the loop at all, and that's also what you want. And if the number of years is 5, we're going to go through the loop 5 times. So in my head, when I write code like this, I think about that. I think about what's sort of the limits of what I care about, and is it going to do what I want it to do when number of years is a particular degenerate case or something. So in this case, we're going to go through a certain number of years, and rather than stopping when our balance gets to a certain level, we're going to stop when we've executed a certain number of years. Although the code ends up being, or the calculation ends up being the exact same, the reason why we're stopping our loop changes. So we're going to take our interest, we're first going to calculate our interest and just get our balance times our rate divided by 100. That'll just be the incremental amount of money we've earned over the course of the year. And then we'll add that to our balance so that our balance gets updated. And then we can see how that works out. So the code for this, let's take a look at that. The code for this is in actually last lecture's code. So if you have that in Eclipse, it's in the previous lecture. So just take a look at what that looks like when we put it into an entire object. Because one of the things that we've kind of separated out two concepts in these lectures, we've been talking about constructing objects, and now we're talking about these loops. Like, knowing how those things fit together maybe isn't immediately obvious, but we use both of them in order to create these applications that we care about. So the one that we're looking at now is investment 2, because what this one is doing is a slightly different task. Let's actually look at the thing that we're going to run first. Let me delete that extraneous and distracting code called park. All right, so here's what we're going to run. We're going to say, what's our initial balance? Okay, well, we're starting with 1,000 last time. We'll start with 1,000 this time. Our interest rate will be 5%. We'll look over 20 years, how much is our investment going to grow? We're going to create a new investment object where we initialize it with the balance and the rate. And then we're going to create this new method, which is called wait a certain number of years. Now notice that by design, we haven't asked wait a certain number of years to respond with the answer at the end. Instead, by design, we've said that the balance is going to be stored within our object after we run that method. And so if we want to find out what the answer is after we run that method, we then have to go in and recover that balance from within our object. We store it locally, and then we can output it here. Okay? So let's just run it, and then we'll see what's happening. Well, no, let's take a look at what's happening, I guess, first. All right, so our object here, our constructor is pretty straightforward. We take in the balance and the rate, and we store it in interest in variables here, just to be consistent with what I'm trying to do with this class using the object-oriented versions. All right, we'll just consistently try and do that everywhere. We're also setting the year equal to 0. We still have the wait for balance method. This is the one that we implemented last time. In this case, we're actually going to continue running until we hit a certain balance, in which case we could ask for what the number of years is when we're done with that. Sorry, I'm going to just replace all the primitive types real quick. There we go. Okay. Cleaning up my code. There we go. All right, so now in our new method, wait for years, we're going to use a for loop instead. We're going to initialize just an index variable I. That's just helpful for us to keep track of the index. We'll go through while it's less than or equal to a number of years, increment it. We'll calculate what our interest is. Let's spell it the right way. At some point, not checking the balance, but just checking whether we've hit the number of years, our balance will be incremented. Those are instance variables. You know, one thing that's not happening here that we're not doing a very good job on is this code doesn't increment the years. And actually, I kind of feel like it should be, right? So if we're going to wait a certain number of years, I feel like we should say year plus plus at the end of this as well, just for the object to be consistent. Okay, well, great, so it's done. Because if you got this object, right, and you say wait a certain number of years, and then you ask get years, it better be the case that years has advanced. Quizzical look, but I think that's right.
I thought it did that last time.
It did do it last time if we called this method wait for balance, because the reason why is because what... Yeah. So in our for loop, we end up doing that, and then what we can do is we can end up asking what our balance is at the end. All right, so we've still got some error because I tried to... Oh, wait, why is this in main? Okay, just get rid of main in our object. I don't want a main in our object. Wow. Okay, great. So now we've got our investment runner. Everything is clear, and if we run this as a Java application, the main function will be run. And we can see that the balance after 20 years is $2,653.30. Different way of looking at it. We started with 1,000 at a 5% interest rate. We could change our constant here to 40. Run that. We'll see that after 40 years, we'll have $7,000. After 400 years, your heirs will have a whole bunch of money. So this is like going back in time and investing a penny in a bank account so that you could be phenomenally rich now because of the magic of compound interest. Oh, and the magic of time travel, but that's okay. So that's an example of a different way of calculating interest that lends itself more towards the for loop rather than a while loop. That code's available for you if you want online. All right, so we're roughly halfway through right now, And what I'd like you to do is I'd like to give you guys an opportunity to just work tangibly with the code a little bit. So I'd like you to create a class that has a main function in it, just so that you have a place to put code. And I'd like you to run some for loops so that you produce the following output. So make a for loop that outputs these numbers as indicated there. And you can do it all in one main if you want. And if you run into trouble, let me know and we can try and debug it. And so what we'll do is, because we're halfway through, we'll come back in, give you 10 minutes to work through this code and 5 minutes to take a break. So we'll come back at 11:25. Sound okay? Any questions online or otherwise before we do that? Anyone? Okay, so we'll be back at 25. What we're working on right now is writing for loops that will output those 5 things, and we'll take a look at the answer when we come back. Stand by. We've got an error in the slide. Error in the slide. Makes a big difference. Try again. Okay, we're coming back in. We have just gone through these different loops, and we've looked at ways in which we could work through them. Some of them are more challenging than others. That first one is real just nuts and bolts for loop, starting at 0, ending at 5. That's exercising just whether or not you can understand the starting and ending conditions and structure the for loop. The second one is recognizing that you can count down, so you can do a minus minus, starting at a high number and continuing while it's greater than or equal to 0 or greater than -1. The third one is executing incrementing by 2, so rather than just adding 1, actually there's a couple different ways that you could do it, but one way that you could do is by taking an index variable that starts at 0 and adding 2 to it in the update round. In the fifth example, actually I didn't look very carefully at the folks in the room. So, like, Lisa, how did you go about doing 1, 2, 4, 8, 16, 32, 64?
I did for integer counter equals 1, counter less than equal to 64, counter equals counter times 2.
Okay, so the key thing that you did was in your update, you did counter equals counter times 2. Another thing that you could have done is you could have had your indices go from 0 to 6 inclusively, and then you could have printed out 2 to the power of your index. Because 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3 is 8, 2 to the 4 is 16. And so another way you could have done it is treated that as a power and just printed out the result of raising 2 to that power. And then finally, doing the characters of string data backwards. We went through that a couple slides ago. If you're watching online, you can go back and look at the exact example. But the basic idea is to make sure that your starting and ending conditions have to do with string data.length with open and closed parentheses, and then making sure that you walk down until you are greater than or equal to 0. And just making sure your endpoints, because if your string is 20 characters long, you want to go from 19 to 0, not 20 to 1. Good?
It also works if you, instead of doing, whatever you're using, integer times 2 for using powers. I thought this would work. I don't know why I didn't try it. You can also use integer equals integer plus integer.
Yep. You could do integer, or you could do index plus equals index.
Yes.
That would do it as well. Yep. All right, the third fundamental loop that exists in Java is not very frequently used, but it is used often enough that we should introduce it and make sure that you recognize it if you see it. And the third loop is the do loop. Now, the do loop is just very slightly different than the while loop. And the reason it's different is because the condition is placed at the bottom, and the loop is launched with the do reserved word. So what a do loop does is it executes the body of a loop at least once, and then performs a loop conditional test after the body is executed. This is often used to validate input, and the reason why is because unlike a while loop, a do loop is always going to run the body at least once. Maybe more, but at least once. That's different than a while loop, because a while loop isn't necessarily going to run the body once. So this code over on the right shows an example of reading data in from the console and requiring the user to enter a value less than 100 before the code continues. So what we do here is we set up something that we haven't talked about in the class, but that the textbook has covered, which is the scanner class. The scanner class is a generic class for reading input from some kind of a stream of characters coming in. And system.in is the opposite of system.out. So system.out is what we use in order to put things on the console. System.in is the stream that we use to get things in from the console. So if we initialize a scanner object by passing system.in into the constructor, the object that we get out, which we reference with the variable in, can be used to consume input from the console as people type it in, as the user types it in. All right, so given that we can get input in from the user using this in variable, we introduce this value integer, and we say, let's do the following while the value isn't valid. So we're going to repeat while the value is bad. So we'll ask the user, hey, please enter an integer less than 100, and then we'll set value equal to the next integer that the user types in, and we'll check. If the value is not within bounds, if it's greater than or equal to 100, then we're going to say, user comply, get back in line, do what you're supposed to do, get in formation. Eventually, the user will comply, eventually, I suppose, and value will now not be greater than or equal to 100, and the flow of the code will be allowed to continue. Now, in this case, we don't end up doing anything with value. This is just an exercise in demonstrating how this works. But following that while statement, you could do whatever you needed to do with value. You could print it out. You could sort database. You can use it as part of a calculation, whatever you're interested in. The last thing there is just a cleanup that we do on the scanner. It is good practice before you end your program to actually close that stream. And that is just to make sure all the system resources that are associated with setting up your stream don't remain open. After your program is ended, this will actually get cleaned up automatically. So I'm just putting this here as good practice for us. Okay, so if we take a look at that code in Eclipse, and I've got that standing by here like a good cooking show. Nope, that's what we just did. Here's the code. You can see the code's exactly the same. If we decide to run this down on the console, it'll ask us to enter an integer less than 100. I'm feeling recalcitrant today, so I enter 212, and it won't let me through. I'm like, okay, fine, 101. Won't let me through. I'm like, fine, an integer less than 100? 100. That's not less than 100. So, okay, 99. In which case, the program ends, and it allows me to go through. So this is just a particularly different control flow structure. If we were to draw this in a flow chart, this would be a situation where the diamond would be at the bottom of our check. We would run the statements before we asked our question, and then we would either repeat or go through our code. An interesting thought experiment then is, if we didn't have this do loop, could we still achieve the same effect? That being ensuring that we're running the body of the code at least once before we exit.
Yeah, you could use a while loop to get input every single time it's not what the desired input.
So let's explore that a little bit. So we could use a while loop. So let's comment this out. So we're going to need to know what we're getting. So we'll have the int value. We'll say while value is greater than or equal to 100, okay, so we're getting an error there because value hasn't been initialized. We have declared it up here, but we haven't actually set it equal to a value. So if we wanted this to run no matter what could we do to initialize value? We want to be sure that we run the code at least one time.
0? Well, no. Yeah, so 100.
So one option would be 0.
Let's do 100.
Why did you switch from 0 to 100?
Because I want to run the while loop.
Right. If we had 0, it wouldn't end up going into the loop because 0 is not greater than or equal to 100. And we would have ended up going through the body of, we would have ended up passing by the loop that starts at 12 and ends at 15 without running that code, and the value would be set equal to 0, and that's not something that actually came in from the user. It was something that we initialized. So by initializing value to something outside the bounds of what is valid, we're sure that we're going to drop into this code at least one time. Another thing we can do in a situation that's a little bit more robust, because let's say we didn't actually have the power to set value before it arrived at this point. So say it's coming from some other process. We could also set up a Boolean variable called first and set it equal to true. And this will be true as long as it's the first time through our loop. In which case we could say, even if Boolean value equaled 0 at this point, we could set up our conditional to use a Boolean relational operator. And we could say while first or value is greater than or equal to 0, we're going to run the loop. All right, so in this case, because first is true when we get to this point, we're automatically going to run this loop. It doesn't even matter what value evaluates to, because we're going to run it no matter what. But if we don't change the value of first, we're going to put ourselves in an infinite loop. because first will always be true because we're never changing first. And because this is an OR relational operator, only one side, the left or the right, has to be true. So for this to function the way we want it to, at the end of this loop, we set first equal to false. So what happens now in the flow through the code is the code is going to get run once because first is equal to true. And then whether or not the code gets run subsequently depends totally on value being greater than or equal to 100, because first is always going to be false, and in an OR relational operator, false isn't going to allow that to evaluate to true. So it ends up just being all dependent on value greater than or equal to 100. So this is a more general way of achieving exactly the same thing that the do loop is doing by introducing this Boolean first variable. Being able to switch between those two is a good skill to have. It's a common thing that you need to be able to introduce, is these Boolean variables that control flow in addition to some other condition that you're interested in.
Can we look at the do loop again just really quickly? I just want to see.
The one down below?
Yes.
Ooh.
Okay, so how does the do loop ensure that the result entered is less than 100?
So on line 25 and 26 are going to get run no matter what.
Yeah.
And then we're not going to be able to get by line 28 unless the value is less than 100. Because
How does the do loop know how to do that?
how does it know how to do what? Check the condition?
Yeah, check to see that it's less than 100.
Well, it's actually checking the opposite. It's saying that if value is greater than or equal to 100, go back and do it again. It's like
Yeah.
go do not go directly to start, do not
That's getting that from, though, because,
go to jail.
there's the while loop below it, but the do loop itself, like in its own brackets.
No, the while is part of the do loop. That's not a second while loop. This is one structure here. This do while loop is one consistent structure. The while is part of it.
Okay, but how? Because it's outside of the bracket there.
Well, when we do it this way up here, the while is outside the bracket also. It's just before the bracket. And now down here, it's outside the bracket. It's just after the bracket. So this condition right here is actually attached to this structure.
It's so weird.
It's a little bit weird.
It's so gnarly. Would it be the
I mean,
same if,
kind of all of this is weird at some level.
Would it be the same if you put the bracket outside of the while loop?
No. Like if you did this,
Yeah.
nope.
What would change that?
Then it would not compile because you need a while after the bracket. And then this would be the equivalent of having, now you have a while loop inside, you have a nested while loop here, where you have a while loop inside your do loop that is doing nothing. And then this isn't compiling because you don't have a while condition on the outside.
So a do loop needs a while loop on the outside to run?
Yes, a do loop needs a while loop on the outside to run.
Oh, that's so weird.
The while is part of it. In fact, like ideally, it would be like this, because then you just have exactly the same syntax as before. It's just the condition is at the end instead of the beginning. But because of the way the parser works, you have to give it some signal that what you're about to enter into is actually a loop. So you do that. Thinking through it.
Okay, so each time it takes the input, runs the whole brackets of the do loop, and then after it's done, it checks the while loop to move forward or to move backward.
It checks if the while, it's just like an if statement going backwards. So if the condition is true, it repeats, which is the same, it's exactly the same structure as if you put the while before. If the structure is true, you repeat. If the condition is true, you repeat. Okay? Okay, so let's see. That's what the point of that was to examine how it is that you could have a do loop, how you could achieve the effect of a do loop if you didn't have a do loop, and that's by introducing this Boolean variable. There's several common loop algorithms that are worth going through. And I want to go through these with you. It's important to know these because so many different practical problems that you run into are just variations on these looping algorithms. I want to go through them with you, but I'm also concerned about making sure that we get our JMonkeyEngine example going. So what I'm going to do is just do an audible here, and we're going to switch over and we're going to do JMonkeyEngine first, and then we'll come back to those loop algorithms as we have time. Because this is going to be the basis of our next homework assignment, I want to make sure that you can get it up and running and understand what we're doing. So just by way of introduction, JMonkeyEngine is a three-dimensional graphics environment. You know, it's typically the kind of thing that you would have in a game environment. It is open source. You can download it. It's specifically for Java. And what else do you know about it? So the project that I'm going to share with you is currently available. It's actually linked in the YouTube video, and it's also linked in Canvas today. So if you need to import it, what you can do is you can download the code associated with that, either the YouTube or the Canvas project, and you can import it into Eclipse, into an existing project if you've got it. But for the folks here in the class, what we're going to do is we're just going to share it via Saros. It's a pretty big file, so it's going to take a second, but that's okay because I can demonstrate what I want you to start with in this example. So let's kick over to Eclipse, and you guys make sure you've got Saros fired up for sharing. I'm not connected, so let me connect. And then what I want to share with you is what we just did here, but let's see, I have an answer to the homework that I don't want you to have, so I'm going to move that. Sorry, everyone. Okay, and that leaves just the test files that we have today. There's no point in sharing those, although I kind of want to keep those around too. Move those out of the way. And that leaves everything we've got left. Okay, great. All right, so this is the project that I'm going to share with you. It's this 10 for loops, and it has JMonkeyEngine involved in it. 10 for loops, there we go. Next. All right, and it'll take a little bit of time in order to connect and then download. Oh, actually, that wasn't too bad. And I'm going to, oh, someone else is bad, however. It's kind of going okay. Let's see, if I can do it, I'm going to restrict to read only. Great. All right, great. So as it comes in, you're not going to be able to edit it until I let go of control. Okay, so where do we start? So there are 4 files here. There is a file called environment. That's actually contains the main function that you want to run. The way this is all structured right now is that it expects whatever code you're going to write to be present in this function called myConstruction. MyConstruction is what you should edit. Box utility is something that I wrote that you're going to call in order to make boxes. But let me just show you what we're doing here for starters. So when we run environment as a Java application, we're going to get a little pop-up window here. This is the splash screen. You have some choices of how big you want the window that it's going to be. You have to choose how large you would like the window to be, whether or not you'd like it to be full screen, and some stuff about color and anti-aliasing, which is getting rid of jagged lines. And then you pull up this image, and what you've got is you've got a game world, and you can use your mouse to zoom out, and you can in theory, you can click and drag in order to see the world that you've got. So that box there, ignore the copyright in the horizon. That box there is a little box that I've chosen to draw through the myConstruction class. So there it is. Zoom in, zoom out. Look at the details. If you would like in myConstruction, if you would like that world to rotate, you can change the function rotate to return true. And if you do that, it just automatically rotates the environment for you. And that's just helpful to kind of look at stuff, I guess. But it can be a little bit confusing when you're trying to build your world to have stuff rotating. So there's the rotating box in the middle of the world.
Is there another little world inside the box?
There could be. Yeah, we never know. All right, so in this environment, the first thing I want to show you is how we're going about drawing that box. So there is a method called draw that is present in my construction, and that draw method is being called by the main method in environment. And when you call it, what the environment is expecting you to return is a collection of objects that it should draw at that given frame moment. And so the way that we ultimately do that is we have to create a new node object. This is a great example of encapsulation and abstraction. What's a node object? We don't know, but we don't really need to know. All we need to do is to be able to create it, to store a reference to it, and then whatever we want to draw, we're going to call this attach child method, and we're going to pass in the thing that we want it to draw. And we could pass in several children, and it's just going to append new objects on the end of it. And after we've attached everything we want to have drawn, we return that node as a result, and then environment is going to draw anything that we find there. So let's go up to what we're creating here. So what I'm doing is I'm creating, just so that we can understand what's happening, I'm creating 6 different variables: x, y, z, width, height, and depth. X, y, and z refer to the coordinates that the box is centered on, like the middle of the center of the box is at x, y, z. And then width, height, and depth refer to, not surprisingly, the width, height, and depth of the box, centered around 0, 0, 0. So for example, if we wanted to have a box that was instead 5 high, we could change 5 here. And because the box is centered at 0, 0, 0, if we want the box to appear to be sitting on the ground, we have to actually lift it up half of its height. Because the center is going to be at 2.5, the box is 5 tall, so 2.5 of the box will go below the center, and 2.5 of the box will go above the center. When we run that, we have a tall box rotating.
There's something very wrong with this game's lighting system.
Well, it's very harsh. Right? It's not a smooth light. Now, the way this is all working is I've created this helpful class called box utility, and it has a static method. And what you do when you call makeBox is you pass in the x, y, and z location of the box you would like to have created, the width, height, and depth of that box. You pass in a file path to the image that you would like to be on the side of the box. And so that's referring over here in the project to this assets folder and this box.jpg file that we've put there. So
Does it put that same image on every corner of the box, or does it take the one image and fold it over into? Oh no.
while you all were working on an assignment, I was busy taking a mugshot of myself in front of the green screen today. And so I'm going to save that into a downloads folder, and we'll demonstrate exactly what's happening. Oops, there's all my email for the world to see. And let's see if we can pull it up.
Just saying it's not gonna fold well.
You're just like in the middle of a sentence and you see the picture and you're like, oh no.
Okay, so now we have this new image that's present in our project, and I'm going to change what's on the side of my box to whatever I just dropped in there, whatever that was. Oh, actually, and let's not distort it.
Oh, okay. Well, that's very nice. It's actually not bad at all.
So now there's a floating box with my face hovering in the world. Oh, everything is good. What more could you want from the virtual world? Now, you know, for something that actually has an image on that, if you start to do things like monkey with it, you know, this graphics as a graphics engine. This has a lot of capabilities, so it doesn't necessarily have to turn out like this. But the way it's currently set up is that it just stretches that image to be the size of the box. So that's just what it is. Okay, but now we don't just have to settle for one box. We can have multiple boxes. So we can add another box here. Let's call it box 2. We need to use a new reference. And after we create box 2, we can drop it in here and add it to the end of our node along the way. And maybe box 2 needs some different parameters. So I'm going to just move these down here because I've already declared them. I don't need to declare them again. I just need to change their value. So we'll put another box maybe at 2, 2. Still make it 5 high. Make it the same. Have it the same image on the side. Actually, let's give it a different image on the side just so we can exercise that.
Why not just make like 20 of them?
Well, stand by. Because we love to have boxes with my face on it. So now you've got 2 boxes in the world. They're rotating around the center. Sometimes when you're building this, it becomes confusing with the rotation to understand where X, Y, Z, and the width and height are. So that's why I gave you the option to turn it off. But, you know, I mean, for what it's worth, you can see the shadow falling across the boxes, which is kind of cool. Now, more generally, you could take this idea, and now we can start to see why you might want a for loop. Now we can think, oh, well, if we were good about our for loop variables, we could actually create a line of boxes using for loops. All right, so what might that look like? Well, let's spare all the images of my face, as much as we like that. And let's introduce a for loop. And let's say we're going to make a bunch of unit 1 boxes that are 1 on a side. We'll have them centered at 0.5 so that the boxes look like they're on the graph. It's up 0.5, but it's 0.5 below and 0.5 above that center, so it's a total of 1 in the height, but it's centered 0.5 up, so you don't want it like halfway in the grass. And what we'll do is we'll build those boxes along, let's say, the x-axis. And so we'll say for x equals 0.0, while x is less than, I don't know, 100. And we'll increment by 3. So we'll start at 0, we'll go to 3, 6, 9, we'll probably end up at 99, then we'll go to 102, and 102 won't get executed because that'll be past the end of the loop. Then internally within here, we're going to create a new box each time. Let's call it box because now calling it 02 doesn't make any sense. But we also need to attach it to that node. So we're going to move the reference to the node above our loop, and we're going to move the attach object here and attach that new box that we create each time. So each time we go through the loop, we're going to create a new box, but one of our loop variable is actually going to be part of the initialization of that box. When we get it back from the box utility makeBox method, we'll add it as a node to our child. And then we'll go ahead and draw that. So now when we run it, we see a whole string of them going off into the horizon. I think if I figure out how to manipulate it. Whoosh. Some sort of radar screen.
It's like a big clock.
A huge clock. Well, what would happen if instead of doing x plus 2 we did x, or x plus 3 we did x plus 2? We didn't change the upper bound. Now they're a little bit closer together. We know they're each 1 on a side, so if we wanted to put them right next to each other, we can make it x equals x plus 1, but of course that wouldn't look any different than a big box. So let's make it x equals x plus 1.1. So they're just ever so slightly have a little difference between them. You can see that working. All right, well, they're all, you know, you've got the 0 point. I would actually kind of like to get them centered on that 0 point. So rather than going from 0 to 100, what I'm going to do is I'm going to go from minus 50 to 50. And I want a little bit more space between them, so we'll make it 1.5. Now, because we start our x position at minus 50, the rotation is going to look more like a fan than a clock. Like it kind of looks like a Cirque du Soleil rockets or something. Well, there's no reason why we just have to modify the x variable. We can also modify the y variable. What's that? Well, circle would be, we could do a circle. You'd have to add some trigonometry in there to get the position of each one. Before we do that, what I want to demonstrate is I want to demonstrate a nested loop. So a loop within a loop. So what that's going to look like is this. And in the interior loop, I want to modify the y variable. So what this is going to do is it's going to run the outer loop from minus 50 to 50. But for each iteration of the outer loop, it's going to do an entire iteration of the inner loop. So it's going to go at minus 50, when x equals minus 50, it's going to do a whole round of minus 50 to 50 on the y-axis. Good catch. A lot of boxes. Maybe too many boxes. It's underneath the world, but looks like Minecraft gone bad. So what's happening here? What's happening is, let's see, I wish I could get to stop. See if we can get to stop rotating so I can sort of point out what's happening. We get to stop rotating by doing false, but I'm not sure we're going to get a good view as a result. The software allows you to do that, but this particular instance of the software doesn't allow you to rotate. All right, but I can zoom out and I can fold it down just a little bit. All right, so what you're seeing here, maybe down here at the very end, is x equals minus 50. And in that outer loop, when x equals minus 50, we're going to do an entire round of y loops, which is going to take us up one column. And when we've done an entire round of y loops, and in fact, since we're going minus 50, those are going to exist down below as well. I can't see if I can get us underneath the ground. So you can see, actually, because y is minus, we've actually got a whole bunch of squares that are down there also. See them extending below. And so this maybe is x0, and this is x1.5, and this is x3 maybe, and this is x4.5 or 3, and then 4.5. And each time we have that outer loop, we're doing an entire run of the y loop as well. And so that's a little bit different than just doing a single loop, because a single loop is drawing a line. But if you do a nested loop, it ends up creating a square. And so there's no reason why we couldn't do a triply nested loop as well. But because we're taking up so many boxes, let's shrink it down a little bit. So now for every x, we're going to do a y. And for every y, we're going to do a z. So instead of doing just one line or two lines, we're now going to do three lines. So what do we expect we're going to see? A cube of cubes. That's right. There we go. Well, I shrunk it down. I reduced the numbers. And it extends below because we have y going to a negative number. If we instead made it y equals 0, y is less than 10, then it's just going to extend above the line. And as long as we're at it, for our last example here, we will make this equal to true. So there you go. Cube of cubes, because you've got triply nested loops. Now, when you're in a visual environment like this, you can see how that triply nested or that doubly nested loop works. It's a little less clear, a little bit harder to understand what's happening when you're working with abstract data. But a spreadsheet, for example, that has rows and columns needs a doubly nested loop. Or if you want to do a table of some kind, that would require doubly nested loops. And actually, I can't resist. I have to run it one time. My mug on the boxes. Yay! It kind of matches. It's the Borg. What more could you ask for in a piece of software?
You could ask for them to be
Animated. I could be like ask for the class to be broadcast live on the face of every one of those boxes while I'm actually gaming. That would be hardcore.
What if you had all of them be GIF images of you saying like a line of script, and then in the background you have like a sound playing you saying that line, but then for every time you say that sound, you have it slightly change the pitch, so it sounds like there's just like 1,000 of you saying like that.
Sounds like Laurel Yanny. Laurel Yanny. Laurel Yanny.
It's a bunch of little.
I only hear Laurel.
Same.
I cannot hear Yanny. New York Times has a slider where you can adjust the pitch of it, and I have to throw it way over to the side to hear anything close to Yanny. It doesn't even sound like Yanny to me. Yanny people are wrong. Okay, so what we did is we looked at nested loops, and we did that by looking at a grid in JMonkeyEngine. Our textbook has an example of printing out a table, which is another thing that you could do with the grid as well. For our homework, what we're going to end up doing, what I'm going to ask you to do is I'm going to ask you to make a pyramid. So take those blocks, lay them out in a certain way so that you get something that looks like a pyramid of Giza or a ziggurat or something. So that's going to take a little bit of thinking about how you're going to pull that off, but it would require your nested loops as well. So in the time that remains, so let's see, how are we doing on the sharing of the project? Did you all get your project to come through okay?
Yeah, yes, it is there.
It looks like everyone is done synchronizing. All right, so I'm going to get rid of my face out of the project, and I'm going to return it back to box.
There are so many uses for that.
I know. And so we're all synchronized. Now I'm going to break the connection, and you guys should have access to it to launch. Again, if you want to if you want to work with this code on your own, it's available from Canvas and from actually the YouTube comments or the YouTube description. All right, but before we're done with what I want to talk about, I want to run through as many as possible these common loop algorithms and do them on the fly. And these are really important because we end up doing variations of these all the time. And so I'm going to create a project where we can, or I'm going to share a project with the folks who are connected so that we can get examples of these. Now, there are examples of these in our textbook, and they're great to study because, like I said, there's just lots and lots of variations of these all the time that get implemented. All right, so the first one is calculating a sum. So let's see, how are we going to do this? We're already sharing 4 while loops, but I kind of want just a brand new one. Just make a new project. It'll be a Java project. And create a new class. And a main and a package.
Hey, do comments in Java make it so that the code knows not to read anything in the comment lines?
Yes.
Okay.
So if something is in a comma, in a comment, the compiler does not evaluate anything in there,
So if you had
with the exception of JavaDoc. JavaDoc, the compiler, or Eclipse at some level is able to figure out what's going on.
So if you had like
Or, I mean, you know, it's got access to the text.
written out in comments,
If you got what?
if you had War and Peace written out in comments, it wouldn't slow down the file from running.
Well, it would still need to process the text, but it wouldn't do anything as a result. So it'd continue scanning down just to find the end of the comment, and then it would go. But it wouldn't slow down. No, it wouldn't slow down the execution of your code, because once it's compiled, all the comments get removed from the code.
Isn't it in Python, like the comments are still read as strings or something like that? Some only like there's
Yeah, depending on how you set it up in Python, the comments are read as a string literal, so that can be a problem. I think that's if you do the triple single quotes, it becomes a problem in order to get a comment. If you just do the single line comments with the hashtag is single line in Java, then it's not a problem. Okay, so we are in Common, and what we want to do here is just get a basic skeleton up here, and that is going to entail a scanner, and we're good to go there, and we're going to close it at the end. And the question is, how do we first calculate the sum of a loop of numbers? Okay, well, we're going to ask the user to enter in a sequence of numbers so that we can calculate the sum. So this is just part of the user experience of this, so that the user knows what's going on. All right, so we'll print out, please enter numbers and Q to quit. And we will say that our, how are we going to do this? Our string will have input, and that will be equal to nothing. And we are going to, yeah, that's fine. Okay. And we will say while in.hasNext, hasNext int. Sorry, getting set up. So now we have a loop. We're prompting the user to enter numbers. The way in.hasNextInt works is as long as the user has typed in an integer, we will get back true. If the user has typed in anything but an integer, we'll get back false. So we're going to continue going through this loop as long as the user types in integers. And as soon as they type in a Q, in.hasNextInt will be false and will leave. Our goal here is to calculate the sum. And so the key observation is that we need to introduce an aggregate variable, which is going to keep track of the sum. And because what we care about is the sum of all the numbers, we know that it's going to start out as being 0. So we're safe initializing it to 0. And we're going to read in each integer from the user. We'll call it x. We'll take in the next number from the user, and we're going to update the sum. And maybe at the end, we'd like to print out what the sum is. Key observation is that aggregation variable. We initialize it outside the loop. We add to it along the way in. So when we run this code, we can type in some numbers, 10, 20, 30, Q, and we end up getting 60 as a result. Okay, so far so good? All right. So that's calculating a sum. The key innovation is keeping track of an aggregate variable. To calculate the average, we have to modify that a little bit. Any idea what we need to modify? Yes. Great. We need to figure out how many inputs there were and then divide by the number of inputs. Well, there's no way to do that after the fact because all we're keeping track of is the sum. Exactly. We also need to keep track of a counter along the way. And the counter is going to be a different statistic that we need to keep track of as we're going through. But the difference is as we increment the sum by the amount that's coming in, we're going to increment the count just by 1. And that's going to reflect the number of things that we've read in. And at the end, we'll say the average is sum divided by count. Now this could give us a slight problem. Any idea what that problem is? 2 problems, actually. Problem number 1 is if the user doesn't type in anything and count equals 0, the result here will be a division by 0 error. So we don't want to do that. The second problem is that if this is an integer and this is an integer, we're going to end up doing integer division, and it's not actually going to be a precise average. It's going to end up being rounded off. So what we're going to do is we're going to wrap this with if count not equal to 0, so that we don't do the division unless we have gotten something in, and we're going to add numerator, denominator. We're going to convert the count into a double by adding 0 to it, 0.0 to it. That's going to upgrade.
Dividing it by a double is enough to turn the whole thing into
Yes.
Okay.
Yep. If there's a double on either the numerator or the denominator, that gets upgraded into a
So it's
floating point.
superior to integers.
It is only superior to integers if you want as precise as possible end result. Depends on your definition of superior. So now we have a slightly different problem. And we get that the average of 10, 20, and 30 is 20. Pretty good. Last time we got 60. This time we got 20. We're calculating different things. So what was it we had to change? Well, in addition to keeping track of the sufficient statistic of the sum, we also had to keep track of the count in order to go through and do the division at the end. But there was a little complexity and error checking because we had to make sure that we didn't divide by 0 along the way. Okay, how about counting matches? Like, perhaps we would like to count how many capital letters there are in a string. That would be something we might be able to do. Although, to be honest, I'm not 100% sure if I can figure out what a capital letter is in international characters. So how about if we just calculate how many times capital, how many, boy, I don't know. Let's calculate how many times E appears in a string on the fly. So this has a slightly different flavor, but not totally different than what we just had. We'll start with our average code. Let me comment out the average code. And now what we're going to do is we're going to count matches. Ah! Wow. Come on, work with me. All right, that's what we're going to count. Wow, that was hard. We're going to need something to keep track of. And in this case, what we'll do is we'll walk through each of the letters of the string that we're concerned about using a for loop. So for example, int I equals 0, while I is less than input.length, do I++. So we'll go through each one of the characters in turn. But what's different about this example here is we're going to do an if statement around each before we do each count. So we'll say if input.char at I equals, oh man, end of the lecture, my typing's getting really bad. Whoa. Come on. Whew, that's tough. All right, so what did we get? We have an error here. We must not have an equals method. We'll just do it. Single quotes in Java indicates a character rather than a string, so it's a different type. So what are we doing here? We're starting with a string, which is a bookkeeper. We have a sufficient statistic, which is count. We're walking through each of the characters in bookkeeper with a for loop that's been particularly set to start at the beginning and at the end. Rather than adding one to count each time through the loop, we're only adding count once when the condition is met, which is that the character is equal to E. And the result is we've gone through all of our data, and we're pretty confident that the number of E's in bookkeeper then is 3. Okay? Does that seem okay? So that's 3 different common loop algorithms. There are 4 other ones, and what I'm going to do is I'm going to let you take a look at those as indicated in the book, in the text. They're really useful to know, and it's important that you're able to walk through them and execute them, and that it would be very important for you to be able to repeat those on your own, because not only you just run into these situations all the time where the problem that you're working with is just a variant of one of these common loop algorithms. Okay, so that brings us to the end of today. What have we done today? Well, we looked at while loops. We looked at how they're different from for loops. We looked at for loops and how they're sort of descended from while loops. They do the same thing that a while loop can do, but they do it in a more compact form. We looked at a do while loop and recognized that the difference between a while loop and a do while loop was just whether or not you're going to run the statement body at least once. We switched order there, and we introduced JMonkeyEngine, and we did that because JMonkeyEngine is cool. You can do games and everything else in it. In fact, you can do virtual reality in it, which is something I'm looking forward to exploring a little bit later this summer. But it's also the basis of our next homework assignment, and so being able to work with that and have a copy of that is important. Then we went back, in JMonkeyEngine, we demonstrated how nested loops can create grids or cubes of items. Abstractly, it's grids or cubes of anything, but it's helpful in sort of a visual gaming environment to be able to see those things. And then lastly, we went back and started looking through some common loop patterns. We didn't get to go through all of them. So any final questions before we wrap up for today? Anything online? No. Okay. Well, great. Thanks, everyone. Appreciate your attention. Have a good weekend. See you in 72 hours.